Inner product spaces. Inner products. In our last section, we were introduced to the dot product, and the dot product is simply a special inner product. It's actually the Euclidean inner product, but most often you'll hear it referred to as the dot product. However, it's not the only dot product. So you can have other dot products that are scalars that use the values of the vectors to determine that scalar. And those we will use the notation of UV in these kind of square brackets. That will let us know that it is in fact an inner product, but instead of the dot product, it's some other. So we're going to look at some of those, but before we do that, we're going to take a look at some of the definitions. So first of all, it's important to understand that if you have a vector space, so we've learned about vector spaces. If you have a vector space that has an inner product, it's called an inner product space. So we're going to let U, V, W be vectors in a vector space V and C be some scalar. An inner product on V is a function. So it's a function just like we had before. The function that we had before was U1, V1 plus U2, V2, and so on. That was the dot product, but it's going to be some other function or the dot product that associates a real number with each pair of vectors U and V and satisfies the axioms. So this is going to be some function that uses vectors U and V with the following axioms: that it doesn't matter the order in which you do the inner product. The U comma V plus W is the same as UV plus UW. Now you might at this point be saying, didn't we talk about these already? Yes, we did. We talked about these specifically for the dot product. So these are true for any inner product. So these specifically are true for any inner product, but we've already talked about them for the dot product. Again, if you have a scalar, just make sure that the scalar doesn't get distributed to both values because it is multiplication. And again, we have that V product V is greater than or equal to 0, and if VV is equal to 0, that means V must have been 0. As I said, we don't need to verify the axioms for the dot product or the Euclidean inner product because all of the axioms are satisfied by those properties that we learned. Instead, let's go ahead and verify that we have an inner product that is an inner product space for this particular function. So again, this is not the dot product. This is a different inner product. Notice it's a function that gives us a scalar based on the values of U and V. So that's what we're going to do. So we're going to go through this one fairly slowly. Let's take a look at the first axiom. The first axiom says that I can do the inner product in either order and receive the same result. So if I did this for UV, I would get 2U1V1 plus 2U2V2. That's what my definition says. If I did it in the opposite order, 2V1U1 plus 2V2U2, that is the same. So it doesn't matter if V2 or U2 happen first or second, just because of the laws of multiplication of real numbers. Let's take a look at the next one. If I have U composed with V plus W, is it the same as U inner product V, U inner product W, the sum of those? So let's take a look at just the left-hand side. The left-hand side tells me that I'm taking 2U and then times V1. Well, V1 is actually V plus W, so it's V1 plus W1. And then the next value is 2U2, and then instead of V2, it's V2 plus W2. So now let's take it to the next step. This would be distributive property, so I'm going to distribute this to both of those values. Now keep in mind where I'm trying to get to. I'm trying to get to this. I'm trying to prove this is true. So UV would look just like this. So I want to get 2U1V1 plus 2U2V2. Do I have that? 2U1V1 plus 2U2V2. So I'm just going to write it in a different order. So this is in fact UV, and this in fact is UW, and so I have shown that those two are equal. Now let's do the same with the scalar. If I have C times the inner product of U and V, does it equal the inner product of CU and V? So C and then inner product of U and V would be C as a scalar multiplied by this product, this expression, 2U1 V1 plus 2U2 V2. If I took it times C, I would distribute that C because this is plus on the inside. So distributing the C, notice I've just grouped it nicely. And why did I group it nicely? Because CU1 and CU2 I can replace with CU. So yes, this is in fact the same as CU, comma, V. And finally, I have to show that the inner product of V with itself would be greater than or equal to 0. So let's start there. If I took V inner product with itself, I would get 2V1 V1 plus 2V2 V2. Well, that's the same as saying 2V1 squared plus 2V2 squared. Well, I know when I square something, I'm always going to get a positive if it's a real number. If I take the square of a real number, it's always positive or 0. And therefore, yes, it's always going to be greater than or equal to 0. And the only way for that product to be 0 is if V is 0. I've given you a similar question to try on your own. I would encourage you to look back at the example we just completed together, but really do take the time to work through this one on your own. It's always easy when the teacher puts the answer on the board. You can say, yeah, of course that makes sense. Yes, I would have done that exactly the same way, but you really need to challenge yourself to try this on your own. So when you're ready, press play to see how you did. So for the first one, again, we can see that it doesn't matter if we take U or V first, we're going to get equivalent values on each side. Similarly, for the second axiom, we can do it just like we did on the last one. This one takes quite a few more steps, but I would be distributing that 2U1. Then I would strategically rearrange them because I'm trying to fit them into the UV, UW pattern. And then I can rewrite it because it fits the pattern, UV plus UW. So inner product UV plus inner product UW. Again, for C, I can do it just like I did on the last one, and I can see that it would in fact be true. However, for axiom 4, I can't verify that VV is always going to be positive because, remember, VV, not V dot V, sorry about that, VV would be 2V1 V2 plus 2V2 V1. Now, can I always say that V1 times V2 is positive? No, because what if V is negative 2, 1? Well, then this would be 2 times negative 2 times 1 plus 2 times 1 times negative 2. And that would be negative 4 plus negative 4, which is negative 8, which is less than 0. Here are a few properties and theorems of inner products. We're not going to spend a lot of time on these. Again, some of these match very closely with axioms we've already studied. And of course, we've already looked at the Cauchy-Schwarz inequality, triangle inequality, and Pythagorean theorem in our last video. So this is just saying that those do in fact work on inner products as well. Not just the dot product, but inner products. Just as we did in our last video to find length, distance, and the angle between vectors, we can do the same with an inner product space. So we can see that all of those definitions are to the left, and we're just going to do some practice. I'm not going to spend time going through each of the definitions because we did it in video 5.1. So if you haven't watched video 5.1, I encourage you to do that before you watch this video. So let's take a look at the first one. We're looking for UV. Now UV is always going to be defined for you. The only time it will not be defined for you is if they say U dot V, because that has the standard definition of the dot product. So here we have the definition, and that's saying to take 3 times the first U value, which is negative 4, times the first V value, which is 0, and add U2, which is 3, plus the second v value, or v2, which is 5. So that gives me 0 plus 15, or 15. Next, let's take a look at the norm of u, or the length of u. Now again, it's okay for you to draw. If we're in R2, it's very easy to draw in R2 what we're looking at. And it helps you to know whether what you're doing makes sense or not so much. So u is negative 4, 3. So 1, 2, 3, 4, 1, 2, 3. So here's u. And when it says find the length of u, I could, without using this formula, I could say, well, this is 1, 2, 3, 4 units, and this is 1, 2, 3 units, and using the Pythagorean theorem, 3 squared plus 4 squared is 25, the square root is 5, so that length is going to be 5. And that's all that that formula is telling us to do. It's saying take the first value squared, well, the first value is negative 4 squared, plus the second value is 3 squared. Well, that gives me the square root of 16 plus 9, which is the square root of 25, which is 5. Now for v, v is at 0, 5. 0, 5, 1, 2, 3, 4, 5. So this is 0, 5. Now, without doing any work at all, I should be able to determine that that length is also 5. But let's go ahead and verify using the formula. 0 squared plus 5 squared, that's the square root of 25, because 5 squared is 25, which is 5. So it does make sense that that distance is 5. Finally, I'm going to find the distance between u and v. So that's this distance right here. Let me change colors. A little too much yellow for my taste. Okay, just to make it stand out. We're trying to find this distance. This is the distance between u and v. So it seems like it would be less than 5 just by eyeballing it, but let's go ahead and use the formula. The formula says we're going to take the norm of u minus v, or the distance of u minus v. So remember what we talked about before. We said, hey, if you want to find u minus v first, you can do that. You can say u is negative 4, 3, and v is 0, 5. So u minus v is negative 4 minus 0, and 3 minus 5. And now I'm just finding the norm of negative 4, negative 2. You don't have to do it that way. You can just go straight into it. We're taking the square root, and then I would take negative 4 minus 0, which is negative 4, and square it. And then 3 minus 5 is negative 2, and square it, which is the same thing I would get over here. Negative 4 squared is 16. Negative 2 squared is 4, and so I get radical 20, or 2 radical 5, and that would be the distance between u and v. Orthogonal projections. An orthogonal projection is the decomposition of a vector u into the sum of two orthogonal or perpendicular vectors. So we're going to be dealing with vector u, and I do want to point out before I explain this that in your textbook focuses only on the orthogonal projection, and they might actually use a different notation. I'm going to use this notation just because I find it very clear and easy to use. So when we're finding this, what we're doing is we're finding two vectors that are orthogonal. So if you'll look at my picture, here's my vector v, and then I've got this line that is basically all of the scalar multiples of v. And then I've got u. So u is the vector that we're interested in. And we're saying, let's rewrite u as how many units of v would I need, and then this other vector that's orthogonal. So it's kind of like if I were to shine a very bright light on vector u, I'm saying at what point would this occur, and then what's this distance as well. Now, in your textbook doesn't care about the orthogonal component, the component of U that is orthogonal to V. I do, so you're stuck with me. But let's take a look at how to find this. Now, when we're working with this, it's actually a lot less complicated than it looks. Essentially, we're saying, if I've got this vector U, how could I rewrite it as the sum of some scalar of V, so some scalar of V, plus some other vector that's orthogonal. So I want to write U as the sum of two parts. Okay? And CV is, I'm just using U hat for that. So that's the orthogonal projection of U onto V. So that's the part that your textbook is asking you to find. Now, the good news is all we have to do is know how to find an inner product, which we know how to do. So in order to find the orthogonal projection, we're just going to use this function. Now, if we are to go to the next step, which is to find the decomposition, which is to find the other vector, all we have to do is take this and rearrange it so that we can solve for z. So we're going to take z is equal to u minus that orthogonal projection. This will all make a ton of sense once we do a question. So let's do a question. Hopefully by the end of this example, this will all make a lot more sense. So again, let's take a look at what we have. We have the original vector u, 7, 6, which is here. And then we have v, 2, 1. So v is right here. And remember, we're really thinking about the line that is created by all of the scalar multiples of v. So not just little v, but v times 1, v times 2, v times 3, v times 4, and so on, v times -1, v times 1/2, you get the idea. What we're trying to do then is first find the projection. So the projection we're calling u hat. So u hat is the projection of u onto v, which is, we're using this formula right here. So we're going to take the dot product of u and v. So u is 7, 6, and v is 2, 1. So the dot product of u and v is 7 times 2, or 14, plus 6 times 1, or 6. And the denominator is v with itself, so 2 times 2, or 4, plus 1 times 1, or 1, and then vector v, 2, 1. 14 plus 6 is 20, 4 plus 1 is 5, and that gives me 4 times vector 2, 1, and that gives me vector 8, 2. So that means at 8, 4, goodness, try to multiply correctly. 8, 4, and this is why sometimes it's very helpful to have a picture, because without a picture I might have stuck with 8, 2. 8, 4 certainly is a point on v times some c value. And in fact, that c value is 4, which we just determined. So what we're saying is 8, 4 is the component that is on v, and now we want to find the orthogonal projection. So if you'll recall, what we said was u was equal to u hat plus z. U is 7, 6. U hat, we just determined, was 8, 4. And z is yet unknown. So what I'm going to do is I'm going to take 7, 6, and I'm going to subtract 8, 4, and that's going to give me z, just regular algebra. So 7 minus 8 is -1, 6 minus 4 is 2, so -1, 2 is z. And here's what that tells us. That tells us that from here, from 8, 4, that's not supposed to be a fraction, I apologize. From 8, 4, I can go 1 to the left and 2 up, or negative 1, 2, and notice that does get me to U. These two are the orthogonal components. So if it said find the projection is just 8, 4. That's just this blue segment there. But if they said find both components, the orthogonal component is negative 1, 2. Now I want you to notice, let me redraw that blue line because I drew over it. I want you to notice that this is the same negative 1, 2 where I could create a parallelogram. And I also want you to notice that U hat and Z should be orthogonal, so we can check that. We have 8, 4 and negative 1, 2, and that dot product should be 0. So 8 times negative 1 is negative 8, 4 times 2 is 8, and that is in fact 0, so it shows that those two are orthogonal. In other words, this is a 90-degree angle. Here's one for you to try on your own. I do want to point out that your textbook has some examples using matrices, using polynomials, using calculus, if you can imagine. I decided not to focus on any of those examples for this video, but you can certainly look at those examples in your text. So if you would, press pause, try this question on your own. When you're ready, press play to see how you did. So again, your textbook wants you just to find the orthogonal projection. So that's the easy part. So I guess it's all really easy parts once you understand. The projection of U onto V using the Euclidean inner product. So again, they're just saying use the dot product. We're not going to give you some other definition for an inner product. So using the Euclidean inner product, U with V would be 6 times 1, 2 times 2, 4 times 0. V dot V would be 1 times 1, 2 times 2, 0 times 0. Whoops, I put dots there. They're pluses. And then V, 1, 2, 0. That would give me 10 divided by 5 times 1, 2, 0, or 2 times 1, 2, 0, which gives me an orthogonal projection of 2, 4, 0. Now, if you want to stop there, you certainly can, or you can say, in order to get to U, 6, 2, 4, I had to take 2, 4, 0 plus some other guy. I probably should have written 6, 2, 4 in a different color. So we'll just go back to the same colors I used on the last one, I think. Again, how do I find that? Well, I can take 624 minus 240. I'm not going to rewrite it. So 6 minus 2 is 4. 2 minus 4 is negative 2. 4 minus 0 is 4. So 2 plus 4 is 6. 4 plus negative 2 is 2. And 0 plus 4 is 4. And this would be the orthogonal projection. So here is U. This guy is the orthogonal projection, which we're calling U hat. And this guy was the orthogonal component, the shorter vector that is orthogonal to the orthogonal projection. Up next, orthonormal basis and the Graham-Schmidt process.